We start the introduction to machine learning course of lectures, and my name is Armen Ghambaryan. I am working as a lead data scientist in Develandoo, and I'm also a CEO of Protogen. Let me start from my work experience. Previously, I've been working in Central Bank of Armenia in the monetary policy department. Then I switched to the field of data science because of the several reasons about which I'll be talking about during the lectures, like what interesting parts data science have, why it is one of the most demanded professions nowadays. What can you do with data science, and what is the role of machine learning in data science? So after switching to data science, I started working in Develandoo, where we are like building state-of-the-art machine learning solutions for different industries, including finance, healthcare, also public security, and social media analysis. So let us start with sharing the presentation. Everybody can see the presentation. Let us start from the nature of data science. Like as some of you might know, and for some of you it might be new information who is starting to go deep into the field of data science. It consists of three major parts. The mathematics part, especially the accent is on linear algebra and probability theory. Computer science part, where you need to know several classical computer science algorithms and also the machine learning algorithms. And the domain expertise, that is like your knowledge of the specific domain where you are building your machine learning data science solution. Before going deep into the nature of data science in the context of machine learning, let us briefly go through the history of statistics, like where it has all started and where it is going and where is data science inside that process, right? As you might know, like the mathematical statistics and probability theory started in the field of applications applied in gambling houses. That's where most of the problems in terms of like probabilistic problems have started to emerge, and gambling houses needed to find mathematical solutions for them in order to like build a system, a profitable system. Yeah. After this application level usage of probability theory, it went to more mathematical formalization. Like the matrix theory was developed, the maximum likelihood theory, maximum likelihood principle has been developed at the beginning of 20th century. The arrival of electronic computation has come, and that's where the field has switched from formal mathematics to practical computation, like starting from 1950s. And that's where actually the divergence of the statistics, two paths of statistics has occurred. The first path was like the traditional line of statistical thinking. What does it mean? Traditional line of statistical thinking means that statisticians basically are making the accent on analyzing causal relationship in the expense of the model accuracy. Most of the times they are not interested that the model is like super accurate in predicting something, but more than why the model is predicting this thing in opposite to the other thing. So for example, in the healthcare industry, not only it's important that like you are predicting cancer with like 99% accuracy. But also for doctors, it's important to understand like why this prediction was made based on which factors that were given as an input to the model. In opposite to that, but again, like the divergence is not that strict. But in opposite to that, the data science is mostly concentrating on building highly accurate models and integrating it in production. So it's more related to engineering and computer science than to like pure statistics. But again, like the main ideas of the modeling are coming from statistics. So the revolution of AI actually started maybe at the end of 20th century with neural networks, the backpropagation algorithm, about which I'll talk about later, and the decision tree models, support vector machines, and so on. After all this, what was said, what is data science? Like according to Data Science Association, the definition of a practitioner of a data scientist is the one who uses scientific methods to liberate and create meaning from raw data. So the most emphasis is being made on algorithmic processing of large data sets to extract like the most useful patterns for accurate prediction of future events. In that case, like what is machine learning in the context of data science? So according to, there are like two famous definitions of machine learning. The first one was made by Arthur Samuel in 1959. According to which machine learning is a field of study that gives computers the ability to learn without being explicitly programmed to do that. A more formal solution was, more formal definition was made by Tom Mitchell in 1998, according to which the well-posed learning problem is the following. A computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. So basically, like the more data you give it, the better it starts to learn the patterns and better it is able to perform the task T. There are three different types of machine learning. About the main accent would be given to the supervised learning, because supervised learning is yet the most successful form of machine learning right now. Like it has a lot of huge cases, and all this AI revolution that has been made is mostly related, associated with supervised learning. Then we'll talk a little bit about unsupervised learning and reinforcement learning. What is supervised learning? Supervised learning algorithm takes a known set of input data, a known response to the data called output, and trains the model to generate predictions for response to new input data. So when you are you need to use supervised learning when you have target. So for example, you have images of cats and dogs, and you know the labels that for this image, it's a cat image. The other image is a dog image. You have the label that you are trying to predict. Supervised learning itself is divided into two parts. If your target is a discrete target, then you are going to the realm of classification tasks. If it's a continuous target, then you are going to the field of regression. So the classification of the input data, the classification for the label based on the input data might be of a free form. Binary classification, if there are only two labels, multi-class classification for more than two label cases, and multi-label classification. So what multi-label classification is? Basically, one of the examples, again, going back to this cats and dogs thing. So for example, you might have an image of, you might have an image which includes both cat and dog, or cats and dogs, right? So in that case, you have, the classes are not mutually exclusive. So the occurrence of one class in your input data is not excluding the occurrence of the other class. In case of multi-class and binary, they are self-exclusionary. Again, like the binary classification, you have two classes. In case of multi-class, you have several classes. What is regression in that case? Regression is applied in the case of continuous target, like targets like prices, financial prices, energy production, SAT scores, age prediction, weather forecast. These all are like continuous targets, and they are going to the domain of regression. So the machine learning community, in opposite to more traditional statistical community, right, is making in general more accent on classification problems. So classification problems are more popular in the machine learning community. And what is reinforcement learning? We'll talk short about it. Like imagine, for supervised learning, you have input and you have target. Based on the input, you need to predict the target. But there are some circumstances, as like the case of game environment or self-driving car or some recommender systems, when you are not only interested in this mapping of the input to output, but you are interested also how to manipulate your input to get a specific output. That's like in raw terms what reinforcement learning is doing. It knows the mapping and it knows how to manipulate that mapping to get the target that it wants. In case of unsupervised learning, there are two types of unsupervised learning: the clustering and dimensionality reduction. So the clustering is actually like combining based on the input data. So here again, you don't have target, you have only input, several inputs. So you need to separate based on that inputs the data. Like based on their unique characteristics, you are just doing the grouping of the data. So this, you can see on the picture, the example of two-dimensional clustering problem, where you have only two features, and using clustering algorithms like k-means, hierarchical clustering, you can make these groupings. What is dimensionality reduction in this case? Again, it's unsupervised learning problem. You don't have some target, you only have input data. What you are interested in is that your input data might have some noisy information, like might have some noise, and because of that noise and because of some pattern complexities for your input data, it's a little bit hard to see the real pattern in the data. So what dimensionality reduction is doing, imagine you have like the dimension of 10. It tries to squeeze that n equals to 10 dimension to a lower dimension. Like in this example, we have three-dimensional data. We're squeezing it, transforming it to two-dimensional space, where we can apply a supervised learning classifier, for example, to make an easy separation based on like the line, just a separation line. But in case of three-dimensional data, you are not able to do that because the structure of the pattern is not that evident as in the case of two-dimensional data. So let us switch to this artificial neurons theme and its influence on developing this machine learning field, right? So the artificial neurons were described first by McCulloch and Peets as a simple logic gate with binary output. So there are a lot of signals arriving at the dendrites part, which you can see from here, and then integrated to the cell body. And if the accumulated signal exists a certain threshold that is predefined, an output signal is generated that will be passed on by the axon. Based on this idea, the first like machine learning algorithm was developed by Rosenblatt in 1957. It's called, and the rule of training this kind of model was called the Perceptron learning rule. So what this model is actually that was proposed by Rosenblatt, it's a binary classification task. So you have either, you need to either predict 1, a positive class, or -1 as negative class. And you also need to define an activation function that takes the linear combination of your input data x with multiplying it with a vector of weights w, and z is the so-called net input to your activation function. So our x is our input data. So for example, an image that we need to classify whether it has cat or dog in it, it's our x. The weights are parameters that need to be learned. And based on that learning, then the output of this function would give you the information needed to make the classification. So we have the vector of weights that we need to learn the values for, and input data, and our activation function, which is either 1 or -1, based on the fact whether our z is more than or equal to our threshold or not. This is like the formal definition of the expression of our model. And what we are doing here, actually, if you like see this formula, what we are doing here, we subtract our threshold from z. So here, we subtract our threshold from z, make that threshold go to the right side of the equation. We assign the threshold the notation of W0, times x0, which is 1 in this case. So what we are doing actually is that we are making the threshold equal to 0 by subtracting. Like if z is more than or equal to 5, for example, if we subtract 5 from both sides of this inequality, we'll get the threshold of 0. So in this case, it's just like more simplified version of the previous equation. And again, the learning rule, we initialize the weights either to 0 or some random number. We perform the prediction, we calculate our y hat, and then calculate this delta difference, right? The delta difference is equal to eta. Eta is our learning rate, which is in the range of 0 and 1. We subtract the ground truth. So for example, if yi is our label, the ground truth label. So for example, it's the prediction of a dog or a cat. So imagine like we have an input data and there is a cat on that input, right? So, and if we assign cat equal to the label of 1 and dog to the label of -1, so our ground truth here, in case of cat, equal to 1. Our prediction might be anything. It might be 1 or -1. We don't know yet, because basically what we have done till now, we have just multiplied our input data with some random numbers and summed them up. So if we have made the right prediction based on that, what values these deltas for each of the weights might have? If the prediction is correct, so for example, the ground truth is -1, and we have predicted -1, there is no update, because you don't need to change the weights if everything is perfect and you have predicted the right way. Again, in case of label 1, what is happening? Again, 1 minus 1 cancel each other. We have 0 update here. But what if we do the wrong prediction? In case of wrong prediction, as you can see from this equation, for example, what we are doing, we're subtracting from 1 the wrong prediction label of -1. And what we are doing, we are, the delta of the weight is equal to 2 times eta and our input data, right? So what it is doing, it's just like pushing the weights towards the opposite direction of the prediction. So if we predicted -1, we update the weights times 2 in a positive way. And the opposite is happening. If the ground truth prediction, the ground truth data is -1, and we are predicting 1, in that case, we are pushing down our weights to the negative territory. So what actually this thing is doing, the main limitation of this algorithm is that it's a linear separation algorithm. So if your data is linearly separable, this algorithm would work, as in the case of the first picture that you can see. If it's not linearly separable, as in two subsequent cases, this algorithm would just iterate infinitely, because it won't find the line that will perfectly separate the two classes. So what we can do with that, we can set two conditions, either of two conditions. Either like we are setting that do this amount of, do like 10,000 iterations. And based on 10,000 iterations, just stop. And what it learned, it had learned. So for example, in this case, we can put some line between these classes, right? The accuracy won't be 100%, like in this case, where like they are perfectly separable, but it might be like pretty high, because like the data is almost linearly separable. The other way to stop the infinite loop of iterations is to set some condition. So for example, you might set condition that if the error of, if the accuracy of your model is more than 80%, just stop the iterations. But again, the main limitations of this algorithm is that it's only applied for linear problems. So this is like the big picture structure of the algorithm. You have the input data, you have the random weights. You sum them up, give it to activation function. Activation function predicts either 1 or -1. You compare it with output. If it's correct, you don't touch the weights. If it's incorrect, you you change the weights according to our rule, pushing it either to the positive territory in case of positive class but negative prediction, and negative territory for the weights in case of negative class but positive prediction. What improvements have been made after that? The main problem, again, besides the fact that it's a linear algorithm applied for linear separation, the other thing is that our activation function, you can't calculate derivatives for that activation function since it's a step function. And what we can't use in this case is the properties of derivatives for doing our optimization. I'll talk about that properties a little bit later. So what other models were suggested after Rosenblatt's perceptron algorithm? The Adeline or adaptive linear neurons were suggested by Bernard Widrow and Ted Hoff. And what improvement was made based on that? So again, we have this picture, right? So we have the input, we have the weights, the summation, combination of these inputs, then activation function, which in case of Adeline is just the same as Z. So Fz is equal to Z in the case of Adeline. So again, like from this part and this part, nothing is happening here. Just this part is going to quantizer, because it's an identity function. Then after calculating this sum, we calculate the error, we update the weight as in case of perceptron algorithm, and do this iteration after iteration until it reaches some convergence. So what is the difference here? The difference, if you see from this part, is that we update the weights not after activation function, as in the case of perceptron algorithm, but before activation function. So what update rule we are using? We are using sum of squared errors. A good property for sum of squared errors is that in this case, we can calculate the derivative. And what does this mean? If the cost function is differentiable and our cost function is convex, we can use the derivative information to do the optimization. What is the optimization for this? The optimization is to minimize the error. So imagine here, if we, every time we calculate the prediction and compare it with ground truth, and if they are equal, what will be our loss? It will be 0. So if this guy is equal to this guy, the loss is 0. So what we need to do, we need to change our weights, the way to make this expression as close to 0 as possible. For that, what we can do, we can use the gradient descent algorithm, one of the most fundamental algorithms in the machine learning and deep learning. What it is doing, like the gradient, we just calculate the derivative for the given weight. Imagine like this is our weight and this is our loss function. We need to make the weight equal to the value that minimizes our loss. So in this case, the value is here. What we can do, so the derivative is the like showing the information of the tangent towards our loss function. So it's like corresponds to the angle, the slope of this tangent. The higher the slope, as you can see from this image for the tangent, the farther we are from our desired minimum. So, but when we calculate the derivative and we know this slope information, we see that if this is positive, then we need to make our weights less than it is now. So for this point, for example, our weights are equal to this part, right? But if our slope is positive, we need to subtract some amount to make it less than it is now. Or in the opposite case, when our slope is negative here, what we need to do? We need to push up our weights. How we are doing this? So again, this is our learning rule. It's like the same as in case of perceptron algorithm. What we do now is that we again use this eta, our learning rate, y like minus the derivative, which is like this notation is the notation of the derivative. Why the negative way? Because as I said, like if the derivative is positive, we need to move to the opposite direction, hence in the negative direction. If the derivative is negative, we need to move to the positive direction. Hence every time like this minus signs the direction where we need to move, which is the opposite to our derivative. Like this is like the opened version of the sum of squared errors and derivative calculated, like based on the WJ weight. This is like the formula for calculating a partial derivative from our loss function. And this is to which our weight update is equal to. When we calculate this weight update times this eta, we apply this formula and then recalculate with the new weights. The new weights are being multiplied by input and we have our output. So what this eta is doing in general, this eta is doing the following. Like, as I said, we know the sign, right? And based on the sign, we know where to move. So if it's positive, we know that we need to move to the negative direction of the current weights that we have now. But how much to move? The gradient is not providing that information, like the optimal amount of movement. That's why we are just calculating by using this eta that is in the range from 0 to 1 most of the times. We are just rescaling the magnitude of the movement. We know 100% that the direction is correct, but we don't know how much to move. So in order not to move too aggressive, we set this learning rate to rescale the amount of movement based on the gradient calculated. So if our learning rate, this guy times the gradient, is high, So maybe it's more than 1. What will happen? We will move too much, like from this part, we might move to this part, but we don't want that. We need to incrementally move to the global minima. We don't need these oscillations. That's why our learning rate shouldn't be too small, like almost equal, in case of it being equal to 0. As you can see from here, like if this guy is 0, there is no update. So the weights are not changed at all. If it's too much, the weights are changed too aggressively in order for us to reach the desired minima. So what the stochastic gradient descent is doing? So if we go back to the formula, what this I notation means? I means like from the first to the last data set. So basically, we are calculating the update for the whole data set that we have. A good thing about it is that like the direction of the gradient is representative of is more representative to the true direction that we need to follow. But it is time consuming and memory consuming since we go through the whole data that we have, which is not that efficient. How can we change that? Stochastic gradient descent is doing just that. Instead of calculating the update based on the whole data, we just provide one sample, and based on that one sample, we update it. That's why like it's called stochastic gradient descent, because the movements here are more stochastic than in the case of gradient descent. So what is the difference in terms of the formula? Here it is the rule for our gradient descent algorithm. As you can see, we are calculating this summation means that we are calculating for the whole data. In case of gradient descent, we don't have this summation. It's just only one data point every time. Each time we give the model one sample of data and we make the update. Although stochastic gradient descent is considered as the algorithm that ensures the convergence of the model faster, still like the bad thing about it is that it's too stochastic, because a single data point might like follow the, might result in the derivative that is like too stochastic, both in its magnitude and sign. What we can do, we can use mini batch stochastic gradient descent. What this mini batch learning is doing, like instead of calculating the gradient, again, the magnitude and sign towards which we need to adjust our weights, which were initially made equal to some random numbers or 0. Instead of calculating the weights, the update rule based on just one sample of data in case of images, not just for one image, but for a bunch of images. But again, not for the whole data set, as in case of gradient descent algorithm. Most of the times, like we select batch size of 8, 16, 32, 64. So it's like, this number, like why we are doing this? Because first of all, it's more efficient, because instead of going through just one element, we process the update by several elements using vectorized operations, which is much more efficient than in the case of the stochastic gradient descent with one sample. Besides that, the direction and magnitude of the update rule is not that stochastic in this case, because there are more data samples combined, and they are more representative of the true gradient direction that we might want to have. So these are like the two starting machine learning algorithms, and the main logic of them were applied to design the more modern algorithms that are used nowadays. One of the most famous algorithms, and famous because of its computational efficiency and good results based on that efficiency and simplicity of the algorithm, is logistic regression. Despite the fact that we use the word regression, that, as I said, was used for not for classification problems, but regression problems. A logistic regression by itself is just a classification model. It's just like a little bit misconception about this regression term inside it. It's not a regression model. It's a classification model, which in its initial form is a binary classification. So we have either one class or zero class, or multi-class classification using one versus the rest approach. What this means is that, so for example, you have 5 classes, right? And you might take one class and consider all the rest as the other classes, right? This is like one versus all. You transform the binary classification, the multi-class classification to a domain of binary classification, right? And that's how like you can use transform logistic regression, which is initially designed as a binary model, to a multi-class one. So what we need to know about logistic regression. First, we need to define the odds ratio, which is P divided to 1 minus P. So what is P? What is the meaning of P? It's the probability of the positive event. So in case of logistic regression, we have either event 1 or event 0. The positive event 1 and negative event 0. And we predict the occurrence of the event based on the probability. So the higher is the probability, the higher is the chance that there is event number labeled 1 is occurring. And the word negative or positive shouldn't be associated with something like really negative or positive, because, for example, a breast cancer problem, the same. The positive class is the occurrence of the cancer. And the 0 class is that the patient is healthy. Then we are defining the logit function, which is a function of that probability we are trying to predict, which is just the logarithm with natural base of our odds ratio. The logarithm of P divided to 1 minus P. And what we are trying, so again, we can see here that this is our expression. This is our model. It has like the same structure as our Adeline algorithm or the Perceptron model that we have already introduced. But here, like we assume that this model is outputting this expression. This expression is not like limited to some range. It might be from minus infinity to infinity. It doesn't have a range. So what we are doing here, we are assuming that we predict the logit, which can be any number. Then what we are doing with that prediction? We are using a sigmoid activation function, which has this form. So we calculate, this is our z. This expression is equal to our z. Then we take this expression and put it inside this. So minus our expression. Why we are doing this? Let me go to the board and show you why we need to do this. So if we go back here, so this is our model, right? Transpose of y times x. And this is equal to our, this is equal to our z. So what we can do now, this is our activation function. And we assume that z is equal to log of p divided to 1 minus p. If we put this expression to this function, what is happening here? It's 1 divided to 1 plus e minus log P divided to 1 minus P. So using the rule of logarithms, we can change this E and this expression with places. So what we can do here is that it might be equal to 1 divided to 1 plus P divided to 1 minus P minus L and E, which is 1. This expression is equal to 1. Then what we can do here, we can write 1 divided to, since we have this negative sign here, we can write 1 minus P divided to P. So we just like switched the places. And if we simplify this expression, we have 1 plus 1, oh sorry, minus P divided, here it's P divided by P. So these guys are canceling out and this is going up. So what this actually means now, this formulation, if we assume that our model is predicting the logit, then if we apply a sigmoid function to the logit output, we get the probability. This is the probability of the positive event happening. So let us go back to the lectures. This is our activation function. So irrelevant of the fact like how, by again, our Z is unbounded. It can be any value. This sigmoid function, if you give it any input, has the following form. If for like really negative numbers, it's almost equal to, it goes towards 0. For positive numbers, for large numbers, it is going towards 1. So what does it mean in terms of calculating the error? This is like the big picture of logistic regression. Again, we have the same input, the random weights, the combination of them, calculating the sigmoid function, producing probability, which is, as you know, like from 0 to 1, again, which is according to the sigmoid function property, that it outputs a number from 0 to 1, which we accept as a probability. And then we, based on the fact whether we have calculated it correctly or incorrectly, we update the weights. What is our update rule? So our threshold here, again, like we are this FZ, the sigmoid activation function in our case, is producing the number from 0 to 1. If the number, we say that if the number is more than 0.5, then it's a positive class. If the number is less than 0.5, we are saying that it's a negative class. And in our case, it's 0, so the positive class 1. If the output of sigmoid function is more than or equal to 0.5 or 0 or otherwise. So let us go to the really important concept in the machine learning, which is the maximum likelihood concept. Actually, here is like the logistic function, likelihood function, which is based on the following. So this is like the multiplication of the events. So from the probability theory, you might know that you have, if you have event probability P1 and P2, the multiplicative rule for probabilities for them to happen simultaneously is just, you just multiply them. What the maximum likelihood philosophy suggests. So imagine you have data, some data, right? And some ground truth labels. You assume that what has happened is happening with high probability. So there is a really low probability of something really anomaly happening. So what data we have is representative of the process that we have. We try to assign high probability for the events we know that has happened, because we know that these are the events that has happened, and we are sure like these are not anomaly events, because what is happening in our life is something that should happen, not the things that are like events with like really small probability. They are all high probability events, and we try to maximize the probability of these events happening. And what this expression is doing, it's doing actually that thing. So let me like explain what this is. Our activation function, sigmoid activation function, is this expression. Again, it outputs the number from 0 to 1. If our ground truth class is 1, then this expression would be 0, and this expression would be 1. So we will concentrate on this guy. And the higher is this guy, the better we have made the prediction, because if our ground truth is 1, we want this number to be as close to 1 as possible. In the opposite case, we have our ground truth is 0. This expression is becoming 1. So we disregard this expression. We concentrate on this part in case that our ground truth is 0. What we want to do for this expression to be high. So we want this guy to predict as small of a value as possible, as close to 0 value as possible. And then we just multiply these guys throughout all the events that are happening. So what we are doing is that we are saying that predict high probability for the event that has label of 1, and predict low probability for the labels that have event of 0. We are maximizing the multiplication of all that probabilities. So this is like the logistic cost function with if we analyze it on like a big picture. So what we can do with this expression, it's a little bit complicated for the mathematical operations to be applied on it. What we are doing instead, we linearize it by calculating the logarithm of this expression. Like we calculate the log of this expression. After calculating it, we see like the multiplication operator switch to the summation operator, which is making the calculation of derivatives much easier. And the final step that we are doing is that instead of, so what we need to do for this function is to maximize it. Hence, maximizing the probability of the right event occurring. But we can assign a minus sign to this event. In that case, what it will transform from log likelihood function to the negative log likelihood function. So if we need to maximize this, if we put minus at the beginning, in that case, we need to minimize this, because minimizing this expression means maximizing this expression. Minimizing this means maximizing the probability, the right probabilities of the event occurring. So this is like the derivative structure of our logistic cost function. The derivative calculated based on the partial derivative of our weights, corresponding to our weights. So again, like this is like our log likelihood function, just like for one event. This is like the matrix, the vector notation of our log likelihood function. As you can see from this equation, the first term becomes 0 if our y is 0, and the second term becomes 0 if our y is 1, respectively. So again, like this is the same thing I've been talking about here, just just transformed by applying logarithm and multiplying by -1. Nothing special is happening here. And what our cost function has, what structure our cost function have. So if our class, or if our ground truth is 1, the higher our prediction of our probability, the less is our cost, the better our predictive model. If our ground truth is of class 0, then the less the probability of our predicted model, the lesser is our loss. So the loss is becoming 0 if we correctly classify these classes, and it is becoming infinitely large when we do the wrong prediction. So the moral is that we penalize wrong predictions with increasingly larger cost. Why we are saying that logistic regression is a linear model when we can definitely see that this guy, the sigmoid function, is nonlinear. So what is linear in logistic regression is like the decision boundary. The decision boundary, so there is again just one line separating, straight line separating two classes. Because like the decision boundary formula is our model equation that is equal to constant. Our constant is 0.5, the threshold of our model. But why it's not the same linear model as in the case of regression models, as in the case of Adeline? Because our input is reaching our loss function, which is this guy, non-linearly. So our in spite the fact that our model is linear in input, but the parameter training is made in a non-linear way. So if we compare it with Adeline, here what we see, the parameters like that are here are coming to the model in a linear way since we are using the identity function. So our fz is the same as x0 w0 plus x1 w1 and plus all the rest of the features that we have for the input. For in the case of logistic regression, the weights are reaching this loss function, this guy, in a non-linear way. That's why the properties, the analytical properties that are derived from training logistic regression model are much more complex. And that's why like it's really popular model, and sometimes when you have a problem that you might transfer either to the domain of classification or regression, you choose the classification domain for usage of this kind of complex analytical properties of optimizing the weights of our model. The next topic that is really, really important for machine learning is the bias-variance trade-off. So what the bias-variance trade-off means. As you can see from these three models, what is the problem with the first picture? The problem is that you could just do better job because like the linear separation is not providing highest possible accuracy. What is the problem with the third figure in the presentation? The problem is that you are fitting too much. So this is like the fitting to your training data. But if you are doing like this kind of overfitting on your training data, you need to expect that your model will not predict, will not generalize the same way as it is predicting for the training data. So the test accuracy for your model would be lower. A good compromise for bias and variance trade-off is training the model not as simple to underfit with high bias and not as complex to overfit. And how we decide the complexity? The complexity of the model is based on the number of the parameters we are using and the way we are using these parameters, the non-linearities that we are giving to our model, both from input side and parameter side. So more formally, our bias-variance trade-off can be introduced in this structure. Our expected loss is equal to the square of the bias. The bias is the underfitting part. Plus variance, variance is overfitting part, plus some noise. So our noise is like the implicit white noise that any process has. So noise is not the thing that we can model. It is implicit to the natural processes. So we just skip it. The thing that we want to concentrate on is the bias and variance, since noise is not informative of the process. It's just a noise. We calculate the bias, the square of the bias, based on the our hx is the true function, the true model that we want to approximate with our model. So the higher is the deviation, the expected squared deviation of our model with the true model, the higher is the bias. So if this number is high, that means that the true predictions and predictions of our model deviate from each other. In case of variance, we are calculating the expectation of the deviation of our model from its expectation. So what this means, we are just like from statistics, we are calculating the variance of our model. The higher the variance, the more noisy is our model. So the more is the chance that it will perform well on training data, but because of its noise, it will overfit to our training data, and for the test results would be far less than we would expect if we just calculate the training accuracy. The other thing to know, and important thing, especially in the domain of deep learning, is the regularization. So what the regularization means, it's like the way not to make your model overfit. One thing that, as an advice from a modeling perspective that I can give you is that overfitting is not a bad thing. A really bad thing is underfitting, when your model is not complex enough to catch the pattern of your data. So what you need to do, first you need to overfit to your data. And by overfitting, I mean high training accuracy, but for test accuracy, it might be not as much. And then try to make your model overfit less. Because if you are underfitting, you cannot do anything else, you know? You need to change your model. In case of overfitting, you need to adjust your existing model. Since it's not that it's a bad model, but you are not using it in a best possible way. And the way to prevent this overfitting, one of the best ways to prevent overfitting is the regularization. So there are different kinds of regularization. We would speak about that also in case of digging into the deep learning domain. One of the most popular forms of regularization is L2 regularization, where we calculate the squared norm of our weights. So our weights, again, these are our random weights that are being updated based on our loss. Went through the logistic cost function as our loss function. We have gone through the sum of squared error loss function, and what this expression means inside the loss function. So this is our logistic loss function, as we have already covered, and this is our regularization. This is the regularization parameter. The higher it is, the higher is your accent on constraining your model. But how we constrain our model with this parameter? So what this expression really is, we are calculating the square of this guy, right? So this guy might be negative, might be positive. At the end of the day, this expression is positive. What we are trying to understand is the magnitude of the weights. So in case of overfitting, what might happen? If our weights are not constrained, they can go to any direction and with any scale, any magnitude. That's where we can overfit, when we let the weights to go anywhere they want. When we use the regularization inside the likelihood function, we are constraining the weights not to go to these extreme values, because the higher, the larger are the weights in magnitude, the more is our loss function, and we need to minimize this expression. So our losses are minimized based on this part, which is dealing with the right and wrong prediction, and the second part, which is dealing to the magnitude. We are allowing the weights to go through in order to solve our optimization problem. The next algorithm I want to talk about is the decision tree learning. So decision trees are one of the most popular machine learning algorithms nowadays because of their speed, simplicity, and the possibility of interpretation of your system. So by interpreting, I'm saying like the statistical causal relationship, why we have done this prediction instead of the other prediction. This is like the simple representation of the decision tree logic. So,
sorry, I would hate to interrupt you. I just want to make an announcement to all participants that we will be taking some questions for the next 15 minutes. And you can submit your questions by clicking on the QA link at the bottom of the main webinar screen. And we will be asking those questions live. And also on the half-hour mark, which means in 17 minutes, we're going to take a short 10 minutes coffee refreshing and leg stretching break, and we'll be back after that. So please, Armen, you can structure the themes based on this timeline, if you please.
Okay, thank you. The decision tree, what is it? Like, we are just from a big picture perspective, we are just defining some set of questions, and based on the answers to that questions, we are making the prediction. So here, we need to decide whether to stay home, go to beach, go to running, or go to movies. So in this case, like whether you need to see, like whether you have work to do, or whether there is a coronavirus spreading across the world. If the answer is yes, then you need to stay at home. If the answer is no, you can go outside. Like by going outside, what you can do? If the weather is sunny, you can go to beach. If it's not, you can go running. If it's rainy, well, you need to know whether your friend is busy. If your friend is not busy, you can go to watch movies with him. If he's busy, you might again stay home. So these are like a logical set of questions based on which our decision is made. So mathematically, what does this mean? What is happening in the background? We are calculating the information gain. So I don't want just to dig into more technical details of the decision tree optimization, but you have this information gain, and most of the times from efficiency perspective, we are dealing with binary decision trees. So we only have two childs for a tree, the left child and right child, not like this kind of thing. Because like computationally, it's much more efficient. And based on that efficiency, also like the binary tree implementations are producing much better results in general than these multi-output trees. Non-binary trees, to be more precise. What is like the logic? We are making the optimization based on several criteria. The criteria names are gene impurity, entropy, or classification error. So gene impurity and entropy, they are the measures to grow the tree, to grow this set of answers. But you can't just like infinitely go by growing this number. You need to stop at some point. And the classification error is a measure to decide where to prune your tree. So this is like the formula of the entropy. Like graphically, entropy, gene impurity, and misclassification error have this kind of shape. Like what this information gain formula suggests. what we need to do, we need to maximize this for a tree. For maximizing this, we need to have this guy big enough and this guy's small enough. So when this I, the impurity, is at its maximum, when the probability of when we are just uniformly equally spreading. So we have 10 samples, 5 are going to one direction and the other 5 are going to the other direction based on the question. So the logic of decision trees is the following. You are starting with like super high level questions in order to guarantee this equal spread of your samples, Then, after these general questions, you go more and more deep into a detailed questions to figure out like where these classes belong to. So from this uniformity, you are going into detailed explanation. And by doing that, at some point, your data sample is starting to belong to, is going to belong to one particular class you are interested in. This is like the big picture of decision trees. Again, the mathematics of it is a little bit more difficult than logistic regression mathematics. But again, like for this course, the main goal is to develop some kind of a big picture intuition of what machine learning is and which kind of level of mathematics and more specifically linear algebra and calculus you need to know. So after decision trees, we are going to the model evaluation and hyperparameter tuning part. Again, this is really, really important topic for machine learning and what this means actually. So we have went through these optimization procedures of evaluating the loss function and making the corresponding updates. But at the end of the day, like the loss function is just some number that we need to minimize. It's not in some specific ranges. And it's a little bit non-intuitive to see like whether your model is performing good or bad based only on loss function, loss values, to be more precise. What we need to do, we are just calculating, we are defining the model accuracy matrix, and based on that matrix, we make the final evaluation of the model. So how we do this calculations? First of all, at the beginning, we have our original set of data. What we need to do, we either might split it to training set and test set, which is a little bit incorrect. I'll explain in a moment. The better way to do this split is to split into 3 parts. We have training data, we have validation data, and we have test set. So there are 3 sets that we need to deal with. We train our model based on this part, the first split, the first set based on the split. We train the machine learning algorithm. We evaluate the machine learning algorithm on our validation set. If it's performing well enough, then we evaluate it on a test set. If it's not performing well enough, we fine-tune our model using its hyperparameters. So we are increasing, decreasing model complexity, adding some regularization, and so on. Why we are not splitting only into training and testing set? Because when you validate and change your model, like the information you have in this validation set is going to training set, which you don't want actually to happen. You want the train set to be trained on its own and independently achieve high accuracies. So when you continuously adjust your model based on results on validation set, you are indirectly overfitting to validation set. And the problem, it would be much more severe if you every time evaluate on test set, and that's how the test set information is being leaked into your training set. At the end of the day, if this leakage is occurring, your accuracy metric might be biased, so the real model accuracy might be lower than your test set accuracy. And using the validation set is decreasing this possibility, because every time you adjust based on validation set and you evaluate your model one time on test set. What kind of like splittings there are besides like this more classical split of training data? You might use the k-fold cross-validation split. What does this mean? Actually, you are doing the following. You divide your model on, you divide your the data set into separate equally sized folds. Here, like there are 10 folds, for example, right? You train your model on 9 folds and test on 1 fold. Then again, you train on 9 folds, but test on the other folds and repeat it based on the number of folds you have. For each testing of the fold, you have this error, right? So based on this error, you calculate your average error of the model. So what is the difference between the k-fold cross-validation and like the standard holdout method? Is that cross-validation error is much more unbiased than the error that you might get from holdout method. But computationally, it takes much more time. Hence, you need to take into account your training data amount and the number of testing folds you want your data, the number of folds you want your data to split to, because if it's too much, it will take a lot of time to calculate this validation error. A slight improvement over the standard k-fold cross-validation is a stratified k-fold cross-validation. And in stratified k-fold cross-validation, the class properties are preserved in each fold. That means if that, for example, if there are like approximately 70% of one class in the training data and 30% of the other class, for each split, the algorithm tries to sustain these properties. So you might have 70%, 30% for this kind of split, again, approximately 70%, 30% for this split, and doing this continuously for all your folds. And the other way around to do this cross-validation is the less popular way of doing that, actually, and it is applied for the more large data sets where doing the cross-validation is too costly. So you define two loops for training. First, you define 5 training. In this case, like it's an example of 5 to 2 cross-validation. So you define the 5 sets, and for each set in the inner loop, you optimize the model based on the split of the training data and validation data, and then evaluate on the test set. So what is the difference of this in opposite to the classical cross-validation? Here, you optimize based on this value. Here, you optimize based on the wall data. So you optimize for 2. Here, you optimize on the number of folds you are defining at the beginning. So this is like the faster way of knowing which structure of the model is the best one in terms of accuracy. Then let's go to the metrics part of the defining the evaluation metrics, and maybe maybe we can continue it after the break.
Yes, I apologize again for the interruption, Armen. This is very insightful and interesting. We have a question from one of our participants that came up earlier, 20 minutes into your presentation. Mm-hmm. And the question is that why sometimes negative classes are labeled as -1 and sometimes labeled as 0.
So it depends on the optimization algorithm it depends on the loss function you are using. So it's just like a definition based on the algorithm. If we go back to the Perceptron learning rule, so for Perceptron, the formula for optimization, since we are using the step function, is this one. So if you subtract from 1, 0, you won't get 0 here. But if you subtract from 1, 1, you would get 0. 0. So it's just like based on the formula of optimization you are trying to achieve. In case of, for example, logistic regression, why the classes are from 1 to 0? Because our activation function produces the output from 1 to 0, and our log likelihood function, again, like it accepts the output that is in the range from 1 to 0. It's again like the mathematical structure of the algorithm and its loss function based on which the optimization is being made. This 1 minus 1 actually notation is a little bit old notation and applies basically to perceptual learning rule. Modern algorithms like binary classification algorithms define either 1 or 0.
Okay, thank you very much for the answer. You're open to ask follow-up questions if necessary, and we will take another round of questions at the end of our second part of the webinar. I suggest we, well, it's 3 minutes left until the half-hour mark. Armen, it's your call. If you would like to fill in those 3 minutes with an overview of what you will be talking about in the second half, that might be helpful. And then we can take a 10-minute coffee break and be back at 40 minutes past the hour. Just a small reminder that we are accepting questions. You can submit your questions by clicking on the icon of the Q&A at the bottom of the main webinar window. I hope you enjoyed. Thank you very much. And Armen, I give the floor to you.
Yes, thank you, Sevak. So where we have stopped before the break, we're going to start the explanation of what are the evaluation metrics for our models and how they can be used, how they can't be used in a biased way that won't represent the true value of your model. So first we can start with confusion matrix. What is our confusion matrix? So in case of binary classification, but actually the confusion matrix might be scaled up to multi-class problem as well, but just for simplicity, let's discuss this binary classification with positive classes and negative classes, again, ones, zeros. The row part is our ground truth. The column part is our predicted value. So how do we interpret the confusion matrix? If the actual label is 1 and we are predicting 1, these are our true positives, the positive classes that we have correctly predicted. If our actual label is 1, but we have predicted 0, these are our false negatives. So we predicted them as negative, but at the end of the day, it turned out that they are positive. So hence, they are false negatives. And the same thing, the same interpretation goes to false positives. We have predicted them as positive, but in reality, they are negative. They belong to negative classes. And true negatives, we have predicted that they are negative, and they are negative. Based on these true positives, false negatives, and true negatives, we can calculate specific accuracy metrics. The first one is our error. So how do we calculate our error? First of all, when we sum up all the elements here, these are like the count of true positive prediction, count of false negative prediction. So if we sum up all these 4 cells, this is our training set, the number of training data, right? And in that training set, we calculate the share of false positives and false negatives. So these are the incorrect predictions, the share of incorrect predictions in the overall set of data. The accuracy is either true positive plus 2 negative divided to the whole data, or 1 minus our error. If like we open this error and use this formula, we'll get the same thing here. But Besides that, we need to calculate several different things. So based on this true positive information and positive classes, we can calculate true positive rate, which is true positive divided to false negative plus true positive. False positive rate is the false positive divided to false positive plus true negative. How do we use these guys? So these are like really important accuracy measures. They called precision, recall, and F1 score. What the precision is about? Precision is the number of true positives, the correct predictions, divided to the total number of true positives plus false positives. So if we predict incorrectly a lot of positive classes, so they were at the end of the day negative, but we predicted them as positive, we get low precision. In case of recall, it is equal to true positive divided to false negative plus true positive. So what this is about, we have predicted this amount of correctly of positive class divided to incorrect predictions of negative class. So these are like the positive samples that we have predicted as negative plus the true positive. So actually, what is the difference between the precision and recall? Precision is like sensible and makes an accent on the false positive amount. So if false positives are high, it's bad in terms of precision. Precision is low because the denominator is large. In case of recall, it makes the accent on the maximum number of true positives predicted. So the more are the true positives, again, the less are false negatives. Hence, the recall is going up when you are predicting the positive class much better. Again, like the difference, precision is more accentuates to false positive thing, and recall is puts more accent on true positives. The higher the recall, the higher are true positives. In case of precision, false positives are changing this number. And the F1 score is just the harmonic mean of precision and recall, using them together. Why we use these metrics? We use it instead of accuracy in the following occasions. Imagine you have your data and you have 100 data samples. Out of these 100 data samples, 98 of that are of negative class, like the class of 0, and only 2 of them are of positive class. So if your model learns to predict only class 0, what would be the accuracy of your model? It would be 98%, a pretty good number, right? But not for that kind of problem. 98% for this kind of imbalanced data set, it's an awful result. So basically your model is not predicting anything. The model hasn't learned anything. It's predicting, but it's predicting incorrectly. In case of F1 score and this usage of precision and recall, the F1 score would be much lower because it concentrates on this true positive, false negative. So if you don't have true positive, then your F1 score would be 0. If this guy is 0, F1 score is 0. If this guy is 0, the F1 score is again 0. So accuracy would be 98%, F1 score would be 0. And this is the true measure of your model. That's why, like, when you have class imbalances, and by class imbalances, we mean that the number of one classes are much higher than the number of the other class, you should never use accuracy. You should use accuracy only when there are approximately tolerable amount of either of the classes. Not like exactly 50-50, but maybe 60-40, 55-45. They are like almost equal, the proportions. But in any case, to secure yourself, you can always use F1 score, because F1 score works as in the case of the balanced classes, as well as in the case of imbalanced classes. And here we are discussing only the binary stuff, like we have positive class, negative class. F1 score can be, and as well as precision recall, can be scaled to the multi-class problems as well. How we are doing that is that we, again, use this one versus all approach, one class versus all the other classes. We calculate, in case of micro F1 score, we calculate micro true positives for each particular class and divide to all true positives of all classes and all false positives all of the other classes. In case of macro one, we first calculate precision based on our class and then just average out all the precisions of our classes. So this is like the difference. In some cases, it's better to use macro F1 score. In the other cases, micro F1 score, but still, like, they are definitely better to use than just a simple accuracy metric. The other topics, again, like returning to this metrics theme, there are a lot of other metrics as like ROC curve for binary classification, as well as it can be applied for multi-class classification. But again, this is like the additional these are the additional topics that you need to read, like the basic metrics and their logic, why they are used, why in some circumstances they can't be used, are just like concluded in this part of the presentation. The other important topic for machine learning is an ensemble learning thing. So what is ensemble learning? Before this, we have covered perceptron algorithm, perceptron model, the Develandoo model, logistic regression, and decision tree. They are all single models. But what we can do to make our predictions better? We can do the following. We can take our training set, sample data from that training set, and train one model. Then again, sample from that same data set and train the other model. And we can train like M amount of models, then average out their predictions and make the final prediction. So we can show mathematically, based on some simple assumption of binomial distribution, that ensembles would always outperform individual classifiers. So if we assume that our error is has a binomial distribution and the error of one model is independent of the error of the probability of an error is independent of the probability of error of the other model, we can calculate the error of our ensemble. So not the error of a single model, but the error of the overall set of models we are using. For one specific example, imagine we have 11 classifiers. What is the probability, the error rate? What is the error rate? In case if 6 of them are predicting correct, are incorrectly predicting the, so what is the error if 6 of them are bad? At least 6 of them are bad. The probability of an error, despite the fact that our individual model errors are 0.25 in this example, the overall error is 0.034. Why it is happening? Because like this, combining these all models in one model, it is reducing this error rate through this multiplication. Graphically, this is the following. So when we are saying that our ensemble would outperform individual classifiers, we assume that our classifiers are at least better than random predictions. And by random predictions, I mean that they are like the 50-50 predictions, that the base error is 50%. So as you can see from this graph, as far as our individual models are better than random, our ensemble error is going down. So this is our base error. The less is the error. That means like from this point, the error is less than 0.5. Our ensemble has better accuracy, which is 1 minus error. As far as like the models start to perform less than random, the ensemble error is going up. So as far as you are not like a really bad data scientist who is training the random model, basically, ensembling is always a good idea for you. What ensemble methods for decision trees we can create? These are like the most popular ones: the random forest ensemble method, the bagging method, and the boosting method. We'll cover them in a sequence. So the random forest algorithm, what it is doing, these are like the basic steps of random forest. You need to, the goal is to train n amount or m amount of decision trees, not a single decision tree. What we are doing, we are making the bootstrap sampling with replacement. And what it means, like with replacement, that means that we have a training set, we take some part of training set, and this is our training data, this part of the overall training set. Then we train the decision tree for that part of the training set, but using not all the features that our training set has, but the randomly selected the amount of features. So imagine like for cancer prediction, we have some specific information about the patient, right? We only take like 50% of that information. There are 10 features that explain the cancer probability. We take only 5 of them. Then after training the model, for the next step, we again bootstrap sample, but with replacement again. What does it mean? For the first step, when we sample the data, we have put the data back into the training set. What it means that for the second step, for training another decision tree, there is a chance that you might take some of the same data samples that were used for the first decision tree. So with replacement is just that. Every time for the next sampling, the probability of taking one particular sample is the same, is remaining the same. Nothing is changing, nothing is conditional. The same data can be put again. And after training like this m amount of estimators of decision trees, you just do like the averaging of the predictions and make the final prediction. So for random forest, what is important to know, and most of the practitioners who hasn't read the paper, the original paper of random forest, doesn't pay attention to that. The interesting part is these parameters, like how much data for individual decision tree to take, how many features to take, and how many estimators to calculate. The number of estimators is one of the most important parameters, actually, because if you take too much of the estimators, you might overfit. If you take less than optimal amount of estimators, you might underfit. So this is like the hyperparameter you need to play with. For the rest, like this is like, yeah, the general structure of random forest. You take the data set tree, train one tree, then train the other tree, then the nth tree, and then you average out and make the prediction. Hyperparameters for tuning. For number of data samples, a good trade-off is considered taking the whole data every time. So scikit-learn, one of the most popular machine learning frameworks in Python, uses all the training data for training individual models. This is like a good trade-off for bias variance. And what about the number of features? So based on the original paper, the number of features taken randomly for the training of the individual tree is equal to the square root of the overall number of features in the training set. This is like the default that scikit-learn is using again. And these are like really good trade-offs. And the only thing, not the only thing, but one of the basic things you need to play with, again, is the number of these estimators. Because depending on that number, you might get different results. What is bagging in this case, and what is its difference from random forest? The bagging is again an ensemble technique of combining the classifier. Again, we are doing this bootstrap sampling. So these are our data sample indices, right? So again, sampling with replacement. What does it mean? The bagging round one takes the first samples from our data set. As you can see, there might be repetitions. there might be repetitions. So the same data set might be taken 2 times for this round. Why is it so? Because like first time we randomly sampled some index, right? Like index number 2. It is in the training set for one individual model, right? Then we put that index back to the sample indices. So the next sample that we are taking has equal chance of taking any of the values, including the one that was taken for the first sample. So this is like with replacement sampling that is applied for random forest as well. There is no conditional probability for sampling the next data point, because the next data point is equally likely to be any of the data points sampled previously. So we train the models and we get the this M amount of models, we average the predictions and make the final prediction. So what is the difference between random forest in this case? Again, we have this number of estimators. We are sampling the same way as in case of random forest, but the major difference and the one that makes actually random forest kind of a better approach than bagging, at least based on the results that random forest is providing, is sampling randomly the number of features, this deep parameter that is being used for random forest. So here, every time we are using all the features from the training data. In case of random forest, we are only using some part of the features and we are doing it randomly. That's what makes random forest really robust against overfitting. And last but not least, like in my opinion, one of the best algorithms for dealing with non-perceptual data. And by non-perceptual data, I mean like the ones that we are that is not being obtained by the sensors visually or by hearing. So for example, the images, the visual images, they are all perceptual data. The audio data is again perceptual data, but the tabular data, for example, the data that we store in SQL tables for some financial data, again, healthcare data and so on, they are all non-perceptual data. So what I mean is that boosting is one of the best, if not the best approach for dealing with tabular data. And why is it so good, and why is it good especially in case of imbalanced data sets? As I said, like imbalanced data sets are the data sets where the class proportions are not equal. This is, for example, true for healthcare data most of the time, because the number of like cancers, melanoma cancers, for example, is much smaller than benign lesions. Or the financial credit risk scoring, which, for example, the protogen is basically concentrated on. The advantage of boosting is that, imagine you have these class imbalances. The first round of boosting, your model learns how to predict the class that is overwhelming in the data set. But for the next round, it assigns much more weight to the error of the classes that are misclassified. So what does it mean conceptually? This means that for each next round, you are learning on your mistakes. For each next round, you are concentrating on your mistakes. What it looks like at the end of the day is that you are concentrating after several rounds of training the decision trees on the classes that are most hard to predict, which in case of unbalanced classes, most of the times are these imbalanced class data samples. So based on learning on your previous errors and based on scaling your errors accordingly, at the end of the day, you get like M amount of estimators that were concentrating on different parts, on different classes of the data. And then you are making the final prediction using all the data sets, all the training, all the decision trees that were trained on the data. And final remarks on ensemble learning. So ensemble is good. It, as we would have seen, it is guaranteeing the decrease of the error rate if our models are better than random. And if our models are better than random is really like a normal assumption to make, because otherwise it's not model to use for anything, for production especially. But the problem of ensembling is that instead of one model, you are using several models. So accuracy is good, but what if the time and memory consumption of that ensemble of models is too much? In that case, like you have super accurate model, but in reality, you cannot use it. So there should be a trade-off between like adding every time new models and the time and space constraints that you have for your particular business problem. One of the interesting examples of that problem was in one of the Netflix competitions, where the winner solution had a super accurate model, but it was so big that it was never used in production, basically. So the next topic, and the most fascinating one, is the topic of deep learning. We'll talk about the basic concept of deep learning, basic terminology, and we'll concentrate our attention on how we train the models and on the specific type of neural networks that are most of the times considered as the main reason why deep learning has become super popular and has overshadowed all the other machine learning techniques recently. These are convolutional neural networks. So let's start in general from deep learning. How can we define it? It can be understood as a set of algorithms that were developed to efficiently train artificial neural networks with many layers. And the basic concept behind artificial neural networks was built upon hypotheses and models of how the human brain works to solve complex problem types. So it's not like directly transferred like these workings. We try to, deep learning in general, like tries to approximate some intuitions and some basic structures of how our brain might work, because we don't know 100% the workings, but we try to approximate, we try to mimic it. So again, it's like a statistical mimicking of how the brain works, but it's not the same. It's not the biological, some process of biological neurons that we try to copy or doing something like that. It's just conceptual, statistical approximation, mathematical approximation to that processes, which we don't know 100%, of course. So what is the difference between the multi-layer models and multi-layer perceptron in this case, and the Adeline model that we have covered already? So Adeline model has this structure, as you already know. The input, the weights, there's vector multiplication, identity function, activation function, unit step function, and prediction. The multi-layer perceptron is doing the same thing, but with several layers. In this case, one hidden layer. So we do the first layer, then the second layer, and then prediction. The third layer is our output layer. What it gives us, and when we started to use this technique. So to understand this, we need to go through the history of evolution of artificial neural networks. We covered this McCulloch and Pitts neurons. We covered the Rosenblatt perceptron model. We covered the Adeline. What has happened then? What has happened is this multi-layer approach. But multi-layer approach has one problem. It's hard to train these kind of models. How we need to train these models, and how can we make them nonlinear? Because as we have seen, the Adeline is a linear model. It cannot learn the nonlinear patterns. Because of these difficulties, this winter of AI has occurred until 1980s, where one of the godfathers of the modern AI, Geoffrey Hinton, reinvented the backpropagation for training multi-layer perceptron networks. So it's like the gradient descent approach applied to training the neural networks. Gradient descent, like it's a really simple approach, but it was hard to imagine and hard to believe that it might be useful for training such a complex system of multi-layer system of model. Then in 1990s, Vladimir Vapnik has introduced the support vector machines, and they were till like 2006, 2010, they were considered as like the state-of-the-art models for many, many tasks. Till 2010, before that, like because of deep belief network models, these artificial neural networks were renamed and there was a remarketing thing actually happened. They were remained as deep learning that defines like all the set of algorithms that we need to train artificial neural networks. It happened in 2006, and in 2010, the real revolution of AI and deep learning has happened. There was this ImageNet, sorry, not in 2010. In 2010, the ImageNet competition has been organized first, but the real revolution happened in 2012. Well, where a group of one of the best deep learning practitioners, in particular Krzyzewski, Sutskever, and Jeffrey Hinton, they have created a convolutional neural network that used the dropout and ReLU activation function, about which we would talk about. They trained it on graphical processing units and achieved much higher results, accuracy results, than all the rest of the models. And that's when everybody started to speak about the deep learning and its power. Why do we need for nonlinearity that we didn't have in case of add-a-line perceptron or logistic regression? So, as we can see from this XOR problem, a famous problem in machine learning community, you cannot do a separation of these two classes because there isn't any line that you can put in order to classify with 100% accuracy these guys. So what we can do, why adding another hidden layer isn't doing anything in terms of linearity of our predictions of our decision boundary? Because like mathematically, imagine that we have one hidden layer, right? And this is the equation of one of the hidden layers. This is the second equation of the hidden layers. And the output of the final layer, if we use, sorry. Okay, sorry for the delay. We can continue with the presentation. What is happening here? We can just use these hidden layers, put in the final layer for prediction, and gain this output. So what this expression means, and why the decision boundary is still linear? Because like we can, instead of writing this weight, we can write just the other weight here, like K1, K2, K3, and K0, and still like this equation is linear in its inputs. So nothing is happening actually by adding another layer in terms of developing some non-linearity. Nothing is happening. Still, we have a linear model. How can we change this? We can use the activation function in the hidden layer that we have already covered in case of logistic regression. I have like explained why logistic regression is not a linear model, because still like its decision boundary is just a plane or a line in case of two-dimensional data. So if we use the activation function after the first layer, and this is like where we put our formula. This is where is our z actually. And then we use the same formula of sigmoid for hidden layer number 2. We then put this data instead of these guys into the final output equation. So what we can see from here? We can see from here that there is definitely a nonlinear relationship between input, parameters, and the output. Hence, the loss function hence the decision boundary, which would be nonlinear in this case, definitely nonlinear. And what this nonlinearity in terms of XOR problem is giving to us? It's giving us the following. Instead of the line, we can do this kind of separation, and we can achieve super high accuracy by using this non-linear structure of our system. And the only thing that we have done is that we have added a sigmoid activation function in the hidden layer. If we don't have this hidden layer, we have logistic regression. That's why like the neural networks are like very simply saying, it's like a bunch of logistic regressions combined. But logistic regression has only one hidden layer. That's why it cannot be nonlinear. Neural networks with their hidden layers and activation functions inside them can be nonlinear. And they can be super nonlinear and can learn super complex patterns. So how do we train the neural network? We use the forward propagation and back propagation. And what it really means is the following. For forward propagation, we are starting at the input layer. We forward propagate through all these hidden layers till we get the output. Based on the network's output, we calculate the error and apply the same stochastic gradient descent. But in this case, because we had several hidden layers, the number of parameters is much more, and these partial derivatives should be calculated for all of the parameters, but the logic is the same. So again, we are using this gradient slope to know how to minimize our loss function. Then after calculating these partial derivatives, we do this back propagation. Again, the logic is similar to the logistic cost function we have covered. We just calculate the parameter derivatives here, and then based on the derivatives, update that particular parameter and do it for all the parameters. The same regularization and more specifically the L2 and L1 regularization can be applied. So we haven't talked about L1 regularization. It's just the module of the weights. Here we just calculate the square of the weights. But in any case, like both negative and positives are going to positive direction. So here, in both of the cases, we are interested in the magnitude of the weights. The same way as we have done for logistic regression, we can put this expression in the loss function, and what it is doing, it is constraining our parameters to go and get some extreme values. Again, like beside this constraint, we try to predict our ground truth, our labeled data in the best possible way using logistic cost function by minimizing this expression, which, as you might already remember, is the same as maximizing the probability of the data events that we have now, because we assume that what has happened should have happened with high probability. So this is like just the backpropagation logic. Again, calculate partial derivative based on the layer and the unit of the weight that the weight is belonging to, a partial derivative of our loss function, and then make the update. Again, the big picture is the following. It's not like that hard, and the mathematics behind it is really like simple. What is not simple is that how you need to choose the right architecture for your problem, how you need to make the model not to overfit or not to overfit using regularization and some other techniques that I'll cover in short. So this is our big picture of the backpropagation, how it works. This is our networks. We give the input. This is the first layer transformation, then the second layer transformation, then this is our prediction. We give our prediction to loss function as well as the ground truth. We calculate our loss using like logistic loss function as we have already shown, and then by using some optimizer, and this optimizer we'll cover in the next part of the presentation. Based on this optimizer, we are doing the update of the weights. After doing the update of the weights, we forward propagate, again calculate the loss, and again use optimizer to update the weights. So this is basically the big picture of backpropagation. Let us now cover the activation functions. We already know the this linear activation function. We know the binary threshold function, which was introduced for Adelaide and Perceptron. So it's like basically our Z, which is the output of this operation, this expression, is 1, for example, if Z is more than K, which is most of the times, as we have seen, where after some simple algebraic manipulations, we make this K equal to 0. And if it's less than K, our Y is 0. This is like the binary threshold activation function. This is the one that we have covered for logistic regression, the sigmoid activation function, which can take values from 0 to 1. The other one is the softmax activation function, which is similar to sigmoid 1, but it is applied in the case of multi-class classification problems when there are more than 2 classes to be applied for. The structure of the loss function for the softmax layer is called categorical cross entropy and is given here. Like basically what you want to do is to, again, like make the probability of your data happening maximum possible. The other really famous function that was used by Hinton and Krzyzewski for ImageNet competition and that have revolutionized how we use modern deep learning models nowadays is the rectified linear unit function. It's like a super simple function, but still it gives a performance boost. And one of the reasons of that boost is that some scientists say that it better approximates the real activation functions that are being applied in our brain. So how our neurons are working, like in theory, they don't react to some noisy signals, like the signals that are not significant. And then after some threshold, they start to react. In case of rectified linear unit, because it's linear, like we react in a linear way. So if our prediction is negative, we say that the Y is 0. At the moment it is becoming more than 0, it is increasing linearly. There are several versions of rectified linear units. Most of the times, like the standard version, just a rectified ReLU activation function is being used. But there is also parametric rectified linear unit activation function and leaky ReLU function, which we'll cover in short. So what is parametric function? So the derivatives in case of ReLU are 0 if this expression is 0, like this guy. If this guy is 0, there is no update. The derivative is 0 as well. If it's not 0, the derivative is calculated accordingly. But in order to make more frequent upgrades, more frequent changes to the weights, we can use this parametric ReLU activation function, which is using the ReLU at the left part. Again, if the expression is negative, it's 0. If it's positive, it's linear. But we also have beta times mean of 0 and z. So beta is a learnable parameter. We calculate the gradients for the beta and update the beta as well. So what the beta is multiplied to? It is multiplied to either 0 if our z is positive, and we have this, so we have ReLU in this case. If our z is negative, this part is 0, but this part is multiplied by the z, the negative value that we have from this expression, times beta. If we choose constant beta of a value, say 0.01, which is like generally the value that is frequently used for the parametric ReLU when we want to transform it to ReLU1. So as I say, the parametric ReLU is transforming to leaky ReLU. So the difference is the following. For parametric ReLU, we are learning this parameter. For leaky ReLU, we are giving this parameter as a constant. The other activation function that is also popular, it is applied in the field of natural language processing most of the time, because in case of computer vision models, deep learning models, you won't see frequently 10H being applied. So 10H looks similar to sigmoid. The range is from -1 to 1, and this is the expression that is used for hyperbolic tangent. And the optimizers, as I said, like the forward propagation goes till the last function. After last function, we have this optimizer. So what this optimizer is actually, we have covered gradient descent already. So this is our weight for the next period. This is our current weight. This is our gradient, and this is our learning rate that we have already covered in case of perceptron, Adeline, and logistic regression. But there are a little bit different ways to doing. This is like the simplest way of doing the gradient descent. We can do gradient descent by using some moving averaging techniques that we'll cover in a short. So first of them is the Adegrad optimizer. Besides this part, this eta times the gradient of the particular weight, we are dividing this to the square of moving average of that particular weight during the training procedure till the point t. So why we can use this Adegrad optimizer? Because sometimes there are some sparse features, and by sparse features I mean that the theta parameter is close to 0 in their case. For these sparse features, they are maybe for some times they are not that important for predicting some values, but they are super important for the other values occurring. So by doing this, you limit the values of the parameters that are growing or that are declining in magnitude, and you are giving more learning possibility for that parameters that are corresponding to that sparse features that fire from time to time, and this firing is quite informative. The other popular optimizer for neural net is RMS Pro, which is opened as the mini batch version of the resilient backpropagation. So what this resilient backpropagation is doing? First of all, you are defining two deltas, the maximum delta and the minimum delta. Our first delta is equal to some value that is in the range of maximum and minimum. Then we are calculating the gradient of two subsequent time periods of the training. If the two gradients are positive, then we update our learning by a factor of 1.2. The update rule is becoming the following. We multiply our initial delta, which is some value, right? That is in the range from min to max, by the factor of 1.2, and we choose the minimum of the maximum delta where we have defined at the beginning of the training, and the delta that we have for the current iteration. And after that, we assign this t+1 update rule for that guy. And if our sign of the gradient is positive, we go to the opposite direction, as we have done for logistic regression. Again, if the slope is positive, we go to negative side. If the slope is negative, we go to the positive side. But if the sign of these two guys is negative, so the sign between t and t-1 gradients for this particular parameter are changing, the one is plus, the other is minus, or the other is minus, the next one is plus, we say that like we need to decrease the learning rate and then reduce the learning rate by the factor of 0.5. And we factor that out by multiplying 0.5 with our current learning rate. Again, we take the maximum value of the minimum delta that we have defined at the beginning of the training, or either the current one if it's not less than the minimum that we have defined, and we do the update accordingly. So why we are doing this? What is the main logic of using these signs to increase or decrease the learning rate? Let us go again to the whiteboard. Imagine this is our loss function. This is our parameter. This is our loss. Imagine it has like this kind of shape. So what we are interested in is going here to minimize the loss to a good minimum. But there is a minimum here as well. So what is happening here? Here, if we draw a line, the slope is positive, right? So when we go to the opposite direction, to the negative direction, here the slope is again positive. So we had plus slopes, right? What we are doing in this case, we are increasing the learning rate. Why we are doing this? Because this accumulation of positive slopes means that we are going to the right direction, and every subsequent slope, positive slope, suggests about it. By accumulating, by factoring, by multiplying the delta by 1.2 again and again, we are like making more aggressive updates to the weight. And by doing that, we can surpass, because we are accelerated here already, we can surpass this bad minima. Here, like the slopes would be plus, minus, plus, minus. If we don't accelerate, we might go here, then here, and we just might oscillate and stop here. But by using this information that all the subsequent slopes are positive till this point, we are already fast enough to overcome this local minima and go to this direction. After we reach this direction, there would be minus slopes and again plus slopes. We'll start to accelerate. And this minus and plus is what our optimizer is doing in this case. Our optimizer is decreasing our learning, our speed of learning, right? Our learning rate, because we are every time multiplying it by 0.5 in case of the optimizer we are discussing, right? So by doing this, these oscillations calm down at some point because the learning rate is going towards 0, and we stop at our desirable minimum. So this is like this was the main logic of our RMS probe. Our probe. What RMS probe is doing. So this is like the 3D example of our loss function. Again, here we need to go towards minimum faster than here, because here we start to oscillate, we decrease the learning rate, and then we go to the desired minimum point. If we didn't do this, you might stuck in some bad minima here. Like it might be a minima point, but it is close to maximum actually. That's what RM probe is not allowing us to do. A special variation of RMS probe is used when we use a mini-batch stochastic gradient descent. As we have discussed already, the mini-batch stochastic gradient descent takes not the whole training data, but some batch of that data. But because of that batch, there is one problem. Our direction and magnitudes are becoming too stochastic. What we can do and what RMS probe is doing, it is rescaling our learning rate based on the moving average of these gradients, squared moving average of the gradients. This is like the formula. This is our current gradient. This is like alpha is between 0 and 1, some coefficient between 0 and 1. This is like the formula of calculating a moving average, right? What we are doing, we like initialize this t-1 for the starting period as 0, and then it starts to accumulate and it starts to calculate the moving average of squared of our gradients. Then what we are doing, we divide our learning rate to the moving average of our gradients. What is the logic of this? Imagine like we're going fast here, and the magnitude of the update is increasing sequentially. Every time it's increasing. we know that at some point we need to stop this speed, because in case of stochastic gradient descent, these directions are not always the right ones. There might be some stochasticity, which is also helping not to overfit actually the model and to reach a better minima as well. So what we need to do by calculating this moving average, we're like calming down this speed of updates, in order when we reach like this part and overcome all these bad minimas, right? For this part not to oscillate too much and to stop at our desired minima. Another interesting optimizer that is used is the Ada Delta optimizer. So the difference between Ada Delta and RMS prop is that besides calculating the moving average of square of the gradient, so this is actually the same formula that we have used for RMS prop. So this is our RMS prop. This is the initial part of our Ada Delta optimizer. By the way, this epsilon is being summed here for the denominator to guarantee for the denominator not to equal to 0 at any time. It's like a small number, like 0.001. So what we are doing here, besides calculating this moving average of squared gradients, as in case of RMS prop, we are also calculating the moving average of our delta updates. So not only our denominator is dynamically changing based on the magnitude, squared magnitude of our gradients, but also our numerator, which is our, in this case, dynamic learning rate, is being changed. So this is like the difference between RMS prop. And the other optimizer, which might be the most popular one, the ADAM optimizer or adaptive moment estimator optimization, is similar to RMS prop or other graph. It's a little bit more advanced actually, because besides calculating the moving average of the squared gradients, it's also calculating the moving average of the gradients itself, right? Then we normalize these expressions. We normalize these expressions based on the denominator. So our beta is an expression between 0 and 1. Actually, the default values, yeah, it's like between 0 and 1, since it's like the coefficient for this moving average. So the more you multiply beta to itself, when it is like in the range from 0 to 1, it is reaching 0 at some point. And like you are calculating in limit, it is going to equal to the expression of m without hat. The same thing is happening for our squared gradients in this case. And the update rule is the following. Instead of using the current gradient, we are using the moving average of the gradient. And we normalize it, we rescale it by using the squared moving average of the gradients. So it's kind of similar to AdaGrad and RMS prop. It's like the upgraded version of two of them. And the last technique that is actually the logic of it we have already covered is the momentum optimization and Nesterov algorithm. So what is the momentum? Momentum is exactly the same logic, the same reason that we have used for doing this acceleration, not to stuck for a bad minima. What we are doing, like we are every time accumulating these updates of the gradients. And then during the update time for the next forward propagation of the weight, we just sum the velocity which was accumulated during this update to the weight update. It's just actually most of the time. So in that case, in case of Ada Delta, we were using just the fact, no, sorry, not Ada Delta, RM prop. We were using just some constant factors to each, every time multiply to the gradient. Here, we are doing the following. We are just calculating the magnitudes and update it based on that magnitudes, not some constant factor as we used in the previous case. So, but the logic again is similar. We accumulate these magnitudes in order to accelerate the speed of convergence to the good minima, not a bad one, which might be close to the maximum of the loss function we are dealing with. And the Nesterov accelerated gradients technique, it's like, again, it's a modification of momentum optimization. And its difference is that we calculate the temporary update based on the velocity information using some alpha parameter. And then we put this intermediate update into the value of the gradient, the formula of the gradient calculated, and then we update it. So in case of momentum, we are using just the previous weight. Here, we are using some intermediary parameter value to update it. It's again, like the difference is not that big. The basic terminology, after like knowing what is like deep learning, what is artificial neural net, and how we are doing this forward and back propagation using optimizers, different kinds of optimizers, and the loss function results we have, we need to cover this basic terminology. So what is the batch size, number of batches, and epochs? The batch size, in case of stochastic gradient descent, is the number of samples we are taking and doing this forward and backward propagation for it. The number of batches is the number of batches available in our training data. So for example, if we have the batch size of 25 and the total number of samples is 100, 100 divided to 25 is equal to 4. So 4 is the number of iterations we can do to cover all the data. It's not necessarily that the ending part of training data should contain exactly the same batch that we're using for the training, because the number of the training data might not be divisible to a number of batches. In that case, we either just skip that incomplete batch or just put it in the training, but like using the different number, the different batch size for it. Which is decided based on this reminder accordingly, right? And the epochs. Epoch is the one cycle of passing through all the data to the network. So when you do all these iterations of batches and you reach the end of your training data, this is your epoch. The deep learning models can be trained for 200, 300 epochs. So you go over the same data, the same overall data set over and over again through these batches. And your epoch is like one-time completion of all the training data, which you come back for the next epoch. What regularization techniques we can use in deep learning? We have talked already about L1 and L2 regularization as like the common regularization techniques, not only in deep learning, but also in classical machine learning. The other ones are the dropout and batch normalization. The dropout is actually a really interesting technique. It's against the conspiracy conspiracy of the neurons. So what the conspiracy of the neurons mean? Because our model is complex, we have a lot of hidden layers, we have a lot of parameters, our model might overfit with its complex structure to the training data and overfit to the noise in the training data that we don't want to happen. What we can do, and by overfitting, the neurons might, like, because they get the input and output from each other, philosophically speaking, right? They are like they might conspire between each other. Like one might use the other's information, and based on that, it might overfit. It's like in financial institutions when financial managers are hiring different accountants that don't know about each other, about activity of each other. By doing this, like, you are limiting the fraud that might occur based on their collaboration against the institution, right? So this is like the logic, abstract logic of the dropout. So what we are doing, we are just randomly eliminating some specific units from the model. And based on that, for each sample, we are eliminating some units with some predefined probability. Every time, this means that every time we kind of have different model for our sample. This is very similar to the ensembling that we have covered, because for this example, like excluding the parts of this elimination where there is no way from input, there is no direct way from input to output. For example, this one, yes, there is no X here, so we can't do this forward propagation. But here we can do this forward propagation because we have at least one X and we have Y. Here we also can do the forward propagation because we have at least one input, hidden layer connecting to the output, right? We can do the same thing for here and here and here. But when the networks are really large and we have lots of hidden layers, there is small chance of this kind of things happening. Actually, you would always have at least several paths that your data can reach to the output successfully. What we are doing, like we are multiplying our inputs, both our original inputs, our X's, and the inputs to the hidden layers with some mask, binary mask, which can be either 1 or 0. And for input layers, this mask is 1 with probability most of the time. We set the probability of 0.8, not for the input data to be eliminated quite often, because like this is the most basic information that we have for the network. But for the hidden layers, again, against overfitting, the probability of our mask times the input for the hidden layer multiplied by 1 or 0 is 0.5. So from time to time, we would eliminate some units of the network, more frequently the hidden units than the input units, because the probability of 1 for the hidden layers is far less than the probability of 1 for the input data. Then the other important concept is the dropout. So what the dropout is doing actually, in the training neural networks, there is this saturation problem, vanishing gradients problem for training the model. And what does it mean? There are some specific zones where your output of the model can reach, for which like there are almost 0 gradients. So there is like, if you have 0 gradient, you are not updating your weights accordingly, right? So what to do not to reach these bad 0 gradient zones? In order to do that, you can just normalize your data. And by normalize, I mean like a standard statistical normalization. The input data minus its mean divided by standard deviation. Plus some epsilon, not again against 0 denominator. So what actually this means? Our inputs are expecting some data distribution. And by changing the weights, you every time change the distribution for the next layer. So at some time, our current layers weights are accepting some specific distribution, but after the update of the previous layers, you are receiving another distribution, which is problematic for a neural network to learn based on these distributional switches. So in order to mitigate with these switches for our model to learn much faster, we just normalize our data. And the normalization is based not only just for calculating the average and standard moving averages or standard deviations of the incoming data. We define the averages and variances, standard deviations that are calculated based on these variances as a parameter. So our model, you are not just giving it some moving average numbers of training samples. You are making the model learn these averages. So what is the best average for your particular input? Then we are also doing this linear transformation after applying this normalization. We do the linear transformation. Again, these parameters are learnable. Then after this linear transformation, finally, we give it to the next layer. Again, like all these parameters are learnable. You calculate the gradients for them. and you update the weight based on them. But what about test time? For the test time, you are not like doing back propagation. For inference, for testing, you are doing just forward propagation. For test time, you are calculating some representative average of your training data. For expectation, for mean of your data, like expectation of the means and expectation of the variances. And this correction factor is used to get an unbiased estimate of the population variance, because like we are calculating this variance based on the chunks of the data. Hence, we need to use this correction factor. Like this is a well-known thing from classical statistics. And after that correction, we are doing this inference. So for training, we update the weights. For inference, for testing, where we are not using any kind of optimization, just forward propagation to get the output, we are calculating some statistics of the averages and the variances using these statistics to do the inference. So what advantages the batch normalization in general is giving? Models in case of batch normalization can be trained faster because of the removal or reduction of internal covariate shift. This covariate shift is a terminology for defining these distributional switches of shifts that are not allowing the network overly to learn fast the mapping of the data. Then the batch normalization also has some regularizing power, again, because it's like this normalization is eliminating the noise intrinsic for every non-synthetic data type. And batch normalization works well with convolutional neural networks. We'll cover right after this batch normalization topic, the convolutional neural networks, where this parameters and in general batch normalization is not applied for convolutional layers, but are applied for subsequent traditional hidden layers that we have covered already. That are like in other way called fully connected layers. So every layer that we have covered till now is a fully connected layer. So what is convolutional neural network or what is convolutional operation in its context? So Sevak, if you want, we can make a short break and then we can continue actually, if that's fine. Sevak, I can't hear you. Sorry for the delay. Let me write to Sevak directly.
Can you hear me now?
Yeah, yeah, I can hear you. So I want to organize a little break. Then we'll cover the final topic of the deep learning, that is convolutional networks.
Okay. In this meantime, can we take some questions that we have received from our audience? Okay, so we have a question regarding about how to get the data samples, I imagine. So the question goes something like, can you please give us small real example output data you worked on?
Like which kind of, maybe the question is related to which domains I'm in and which domain data where I can get to predict the output, right? Maybe
yes.
That. Because one simple example, as in the case of images, is the different sample images, and I need to classify whether there is a cat or dog in the image. This is like a toy example. A more serious example is, for example, the financial credit risk scoring the same. So I have the input information about the customer, gender, whether the customer is married or not, family, some family-related information, phone number, its historical credit rating, and so on. And what I'm doing is the bank, the financial institution, is defining for me the probability of default definition, the definition of default. So the bank is saying, for me, 90-day overdue, for example, is a default, right? Or maybe 60-day overdue is a default. Then I'm saying, okay, then this guy, I know that they had this overdue. I'm saying this guy has defaulted, this guy is okay. Again, this guy has defaulted, the other guy is okay. And then this is like my mapping, the client customer specific information and whether he has defaulted or not. And then I'm learning this mapping, like the factors that are causing the default. After learning, for the test data, again, I have this customer application data, but I don't know whether the customer would default or not. I know it's his historical data, but not whether it will default for the next month, second month or not. Then I use this trained model. I take the input information for the customer and I am predicting the probability of default, which is the number from 0 to 1, using the sigmoid activation function, the same that we have covered for logistic regression and for artificial neural networks as well.
Okay, thank you for that. We have a second question regarding what are some of the more desired essential skills to be a data scientist in the market today? And yeah, and it was also a question about the the career path of a data scientist in Armenia.
So let's start from the career path, maybe. Yeah. So actually, the demand for data scientists is rising in the developing countries, which Armenia belongs to, because there is a shortage actually of data scientists overall in the world. But why this shortage is happening? Because in order to be a data scientist, you need to know, you need to have an interdisciplinary knowledge. So being a computer scientist, a programmer, is not enough. You need to know well linear algebra, calculus, and statistics. That's like a requirement. I'm not saying that you need to be like a god in both of the fields, but you need to have a decent understanding of that field. And the last but not least, you need to know the domain you are working in. For healthcare, you need to know some medical, you need to have some medical experience dealing with diseases. For financial industry, you need to have some domain knowledge regarding the reasons, the macroeconomic factors of the customer or an organization going default or having some risk-related problems, right? So what is the best thing to do is that choose your domain you are interested in, gain domain knowledge, experience, and in parallel, study this linear algebra, statistics, and computer science in order to incorporate these quantitative tools with your qualitative assessment of the domain to make the predictions, to do this causal relationship analysis and something like that. Can you remind me of the first question again, Sebak, please?
Yes, sure. The first question was about asking about the example of data sets and how do you obtain them.
No. After that, you had 3 questions. I have answered to the first one and the last one.
Well, it was actually the same person was asking 2 questions. The first one was specifically about career path in Armenia, and the second one was more general essential skills of data scientists.
Yeah, so I guess I have answered to that. Again, like linear algebra, mathematical statistics, including probability theory, of course, and computer science.
Okay. Okay. And I guess we would be taking a break as you suggested now.
Yes, by the way, I want to add one more thing, that there was a question on the technologies used, whether, for example, Amazon SageMaker is a good one or not, or which stack of technologies we are using. Yes. I want to say that I'll cover that at the end of the lectures. I'll cover the reference list where you can go to after these lectures, and also the technologies that are like the hottest ones right now in the industry. continue from where we started before.
I covered all the basic building blocks for training a neural network. Now I'm presenting like one of the most famous architectures of neural networks called convolutional neural networks. Why they are using, why they are named convolutional neural networks? Because obviously there has something to do with convolutional operation. And again, as I mentioned before, the revolution of AI and deep learning and machine learning in general was basically like 90% was because of the success of convolutional neural networks applied in many fields, but most of the time, like the basic success is in computer vision. Since why it's in computer vision? Because CNNs are specialized networks for processing data that has a known grid-like topology. So what is a grid-like topology? Time series data is a 1D grid. So grid-like is that you can put the values of the data in a grid-like structure. The image, for example, what is an image? It's a grid of pixels, 2D grid of pixels. Again, like this is the main starting point of success of deep learning. 2012 ImageNet competition won by the convolutional neural network model. After that, they have been developed much better models that have achieved even higher accuracy. At the end, the ImageNet competition was the last models that have been created, like in maybe 2050, 60. They were able to beat the human performance in for that task. So what is convolutional neural network? It's simply a neural network that uses convolution in place of general matrix multiplication. And this general matrix multiplication is exactly that we have covered till now. These fully connected networks. We have X and Y. We compute the vector multiplication of them. This discrete convolution can be viewed as a multiplication by a matrix. However, the multiplication is done in a specific sparse way, and which is much more efficient in terms of time complexity and space complexity than the fully connected layer matrix multiplication operation. So this is basically what convolution is doing. This is our input. Imagine this is an image, again, that has this grid-like structure. These are the pixels, pixel information, which are from 0 to 255, but most of the times not most of the times, always we are normalizing these numbers for some specific range, most of the times from 0 to 1. For that, we need just to divide these numbers, all these numbers to 255. That's where it will be in the range from 0 to 1. So these are our pixel information of our image, right? This is our kernel, the receptive field that we are using to give the to make the output for the next layer of the model. So what this kernel is doing? It takes part of the input, this A, B, E, F, and is doing element-wise matrix multiplication. So A is multiplied by W, B with X, E with Y, and F with Z. Then we move to the next part, and this guy, this BCFG, is multiplied with, again, the same kernel. Then the last part, from the from the column perspective, C, D, G, H is multiplied again with the kernel, and we do it row-wise as well, row-wise and column-wise, horizontally, vertically. So at the end, we have this output. This guy, this pixel, a new pixel that is calculated based on the linear combination of the kernel and the input. The other pixel, another pixel, and so the output is generated. So what is the motivation of convolutional operation? Why it is efficient and why it is used in deep learning? So there are three major points that help that make a convolution operation a really brilliant operation for designing deep learning architecture for the models, especially for computer vision tasks that use, again, 2D data topology. These are the sparse interactions, the parameter sharing, and equivariant representations. So we'll cover all of them. What is a sparse interaction? Like imagine for this x and y multiplication, we are using m times n matrix of weights. In case of convolutions, they are decreasing this m number to k. And instead of using O m times n runtime, we are using O k times n runtime. Because k is significantly less than m, the speed of our network for forward propagation and backward propagation is much faster, and the network itself is much more efficient. What visually it looks like we have this output layer and the input layer. This output layer might be the final layer or might be some intermediate hidden layer. So in case of convolutions, the x3 input is being given not to all the outputs because of this kernel of size 3, for example, which is this guy, but with 3 times 3 size. This x3 is being transferred only to S2, S3, S4, not to S1 or S5. This is like this sparse connectivity. In case of fully connected layer, this x3 input is being passed to all the outputs, and all these directions have the corresponding weights with them. So that's actually it. You are like saving a lot of computation by using this approach, because again, the number of directions are much less, the number of connections are much less, but still they are efficient enough to learn really complex patterns without overfitting, and with using this visual way, something similar to the way people visually are analyzing the picture what they see. Sparse connectivity can be viewed from above as well. So instead of S3 receiving all these x's, it receives only x2, x3, x4 because of the kernel of size 3. In case of fully connected layers, all x's are going, and these x's are our number of features. All the x's are going to all the directions. So our S3 is using all the x's, again, with a lot of weights, a lot of memory consumed. But again, an interesting thing about convolutional neural networks is that despite these kind of connections, that like the output is not using the whole input, when you make the hidden layers, subsequent hidden layers, the receptive field of the last layer is much larger than intermediate receptive fields. And by that, I mean that the last layer, as in this case, receives all the x's, whereas the individual hidden layers are not receiving all the x's. But because of this connectivity, and again, remember that the strength of the deep learning models is in their connectivity approach, connectivism approach, which is really a strong one. Because of this connectivity of the units of the neurons, the receptive field is becoming much larger, and all the information is being transferred to the final layers with using far less amount of weights and far less amount of computation. Plus, convolutional operations are highly parallelizable, which from time complexity perspective makes them really good, super approach for training your model.
So what is parameter sharing? Actually, you might already guess that in case of convolutional operation, the central parameter of the kernel, if like there is a free element kernel, the S2 receives, only S2 receives the central kernel. So in case of fully connected layers, like all the outputs are receiving all the weights. And there are like weights for each of the direction. Again, here, the weights again correspond to directions, but there is like a sharing of parameters. The same input uses the same number of parameters for the output. So that's where like less amount of weights are being used. Again, like it is contributing to the overall reducement of the complexity from time and space perspective of the model. And what is equivariant representation? Like this kind of representation characterizes what I mean by this is our free by free kernel. This is our image. So it doesn't matter whether we use convolutional operation to transform this image to that image with this specific number of kernels, which are the parameters of our model in this case. So you'll get the same result as doing this towards this and then translating this 9 a little bit upwards and to the right, as you might do if you translate it to the upper right side and apply convolution. What does this mean? Irrelevant of the position of the value of our interest, and the value of our interest here are these pixels, because for this particular task we might want to predict that this image, the label for this image is 9, right? So it doesn't matter whether this 9 is here for convolutions or here. This is this equivariant representation that really helps to build a model, especially for computer vision tasks. This is like just an example of convolution, like with weights of 1 for free to free kernel. Again, we are receiving this 183, irrelevant whether this data is here in the image. This is like, imagine this is pixel data. It's irrelevant whether the data is here or here. We'll still get our 184. But in slightly different positions, depending on where, but the number, we will get this number. And what are convolutions? What is the output of the convolution? Convolutions are learning to transform the image in a ways that is more easy for the subsequent layers to make the classification. So for example, whether this is a Renaissance photo or not, right? By analyzing its edges, colors, its shape, by using these kernel transformations, it's easier for fully connected layers that are coming subsequently to say whether this picture is corresponding to Renaissance class or expressionist class, for example, right? This is like the big picture structure of the convolutional neural networks. This is like a handwritten digit, for example, as an input data. So the first layers are learning some basic abstractions for the data, some edges information for the data. The subsequent layers are learning higher abstractions that for human eye actually is a little bit different to find the logic in this abstraction, but still the model itself based on optimization makes some useful representation, subsequent transformation and representation of the data that makes it easy for the final layer to say that this image corresponds to the label of 4, for example. And again, let's deal with this, let's go deep into this convolutional arithmetic for deep learning. There is a paper with the same name, and I highly recommend if you are interested in deep learning, learning convolutional neural networks and the other neural networks as well, because most of them are using convolutional operation. I highly recommend to read the paper named Convolutional Arithmetic for Deep Learning. If you search in internet, you'll find it easily. It's a 2018 paper. And actually, I am taking all these explanations from that paper, just like summarizing it. So this is our convolutional operation. This is our data, input data. These are our weights, our W's that we need to use, we need to learn using backpropagation. So we are doing this element-wise multiplications. So we are multiplying these element-wise with these, and then we write the sum of this multiplication. We do the same thing for the subsequent receptive field multiplying with the kernel, and then for the rest. At the end of the day, we get this result. So from this, we get this by using 3x3 kernel. This is our output. These are our weights. We can also manipulate the output that we want from analysis perspective for subsequent layers. How can we manipulate the output? For example, that in this example, we had 5x5 image. We got 3x3 image. What we can do to change this? We can just append zeros from the borders of the image and make it arbitrarily large for the convolution operation, then to get the output that we want. So here, like the basic terminology here, our image size, our input is 5x5. Our kernels are 3x3. Our stride is 2, and our padding is 1. The padding is how many zeros you concatenate from the border side, from both the sides, from column side, row side, from all the sides. The stride, what is the stride? The stride is the number of steps we are jumping through. So here, for example, our stride was 1. See, like from here, we jump to here. From here, we go here. In this case, from here, we jump here, not here, because our stride is 2. It's the number of steps we are jumping towards. So this is like a better representation of the stride. Here, the stride is 2 because it's like 1 and jump here, 2. The same way, row-wise. Here, and we jump here. In case of stride 1, we have this, we go here, and then we go here. What is the difference between the strides? Just like we get different output shapes of the images. And we can get arbitrary number of output channels from the image. So for example, here we have 2-channel image. What's the 2-channel images? It's like just like 2 matrices corresponding to the channels. Most of the times there are 3 channels. These RGB images have 3 channels. Here we are dealing with 2-channel example. So for this 2-channel example, we might define arbitrary number of kernels, 2 for each direction, because we have 2 channels. Then after applying convolutional operations for each of the channel, we just sum the 2 matrices element-wise and then concatenate them. So this number, which is the output channel number, can be any arbitrary number. So you can scale from 2 channels to 64 channels, for example, right? Our example is like 3 by 3 convolutions. We have 3 by 3 convolutions, 2 these kind of convolutions, and we are defining 3 of them for 3 output channels. And the pooling, what the pooling is doing, actually, it's like this kind of similar to convolutions. The difference is that in case of convolutions, we are multiplying the number with the kernel. So here, these small numbers are our kernel elements. Here, the output of this element-wise operation of the input pixels to the kernel. In case of pooling,
you are not multiplying these numbers with a kernel of any size or number. You are just calculating the average of these numbers. So it's like 3 plus 3 plus 2 plus 0 plus 0 plus 1, 3, 1, 2 divided by 9. And we get this number. The same here. You calculate the average of this. Then you calculate the average of the last part and do it row-wise as well. So this number is the average of 0, 0, 1, 3, 1, 2, 2, 0, 0. And you get 1. This is the pooling operation. The max pooling is similar to average pooling, but instead of calculating the average, you are calculating the maximum value of this field, of this part of the image. So the maximum here is 3. The maximum here, this part, is 2. That's why it's 2 here. Here, actually, you can see, like, it's a nice visualization. You can explore. And what translation invariance? So what we have covered till now was equivariant representation. But what is translation invariance due to pooling? It's like actually similar to equivariant representation. So imagine you have this image, and these are the pixel data information. When you do this max pooling with 3 by 3 or 2 by 2 kernel, for example, it's irrelevant whether it's like it becomes relevant when the receptive field of these images are a little bit wide. But for this example, see that it's irrelevant whether our 1080 is here, or a little bit to the right here. Max pooling still gets these numbers, this 180, 180. Again, irrelevant of the position of our object of interest, the pooling operation produces concentrates on that object, irrelevant of its position, and that's why, like, convolutional neural networks are pretty robust to the positions of the objects of interest for us. And then we just, it's a simple arithmetic for what output we get by having the I input size, kernel size of K. So the output is the following. Like, I'll explain it for this simple case when we are not using zero padding. And zero padding, again, I repeat, is the concatenation of zeros for enlarging your picture. So what this number actually is, we can go and like the same arithmetic applies whether we are doing it column-wise, vertically, or horizontally, or row-wise. It doesn't matter whether we are going right or we are going down. The same mathematics, the same formula is working for us. So if we go to the whiteboard, let us clear this. So imagine you have this grid. 1, 2, 3, 4, 5, 6, and maybe this part as well. So 1, 2, 3, 4, 5, 6, 7, 8. 8 cells. And we say that it's the output is equal to I minus K plus 1. And our stride, the jump size, is equal to 1 in our case. So what we are saying, if, for example, so our I is equal to 8 in this case. It's 8, and our kernel, let's say it's 3. So why the output is equal to 8 minus 3 plus 1. Why is it this number? Because, like, this is our first kernel, right? So we go one step at a time. Then we go here, then we go here. And when we say that it's 8 minus 3, which is 5, we say that there are 5 steps to be made. Why we are adding this 1 at the end because we have made the initial step. So it's our initial step, and then 1, 2, 3, 4, 5 until we reach the end. Let us go back to the presentation. So this is actually this formula. The padding, like the padding, we are adding the padding from all of the sides. Actually, with zero padding, the formula is the same, but our image is instead of I, now is I plus 2p. That's why it's like the same formula. If we move 2p here, we'll get I plus 2p, which is the current image size with padding, minus kernel plus 1. So it's actually the same formula, just a little bit modified for padding. Half padding, which is really interesting thing, is when you want your output, and this is really interesting property. Many times you want your output image to have the same size as your input. And most of the times, like the kernel, we are taking the kernel to be a even number, odd number. Why we are doing this? Because like it's one of the explanations if we go to the whiteboard again. Why kernel should be odd? Because odd kernel has this interesting property. Its receptive field has a center. In case of even kernel, we don't have center here. That's why, like most of the times, you will see an odd kernel size because of this center. And this is just a formula. This is actually our padding. Like in order to get the same number of output as input, we need to manipulate through everything through padding. And in order to get this padding, like we have again this I minus k plus 1. This is the same as here, I minus k plus 1, plus our padding, which here is defined to some number. Here, it depends on whether we want the same padding, so the same output as input. So mathematically, if we just, instead of k, which is an odd number that we have defined, if we use 2n plus 1, input it here, we'll get that our output is equal to our input. And if we want our output to be bigger than our input, we can use the full padding formula. Again, this is our I minus k plus 1 plus the padding size. Depending on this padding size, the output is becoming greater than our input. So this is actually the operation. So our kernel is 3 by 3 and our output is this guy. So this is the example of image size of 4, kernel of 3, and stride of 1, and no padding at all here. So why it's 2 by 2? Because 4 minus 3 plus 1 is 2. I have applied just this formula. Just after going through the paper that explained this in more detailed way, just go through examples and just memorize, because the mathematics is really simple, but most of the times it is becoming complicated when you are dealing with a lot of hidden layers, a lot of convolutional layers in the big architecture of the model. And this is the arbitrary padding that we have covered with unit strides. Half padding, again, like we're getting the same output size as input size. This is our half padding. See, we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5 by 5 image, and our output is again 5 by 5. This is a useful property, and it's called half padding or same padding. The full padding is the case where by using these paddings, zero paddings that we concatenate to the image of our interest, we are making the output larger than our input. And this is the last case of the
formula for convolutions where we describe this input and output using stride of 1. What happens when the stride is more than 1? So let us go back again to the whiteboard. Let us clear everything. And again, define our grid 1, 2, 3, 4, 5, so 8, 6. Our I is 6. So in case of padding equal to 1, we were doing this, right? This step, then this step, and then the rest. In case of padding, for example, equal to 2, we jump one case. So instead of doing this, we are doing this guy, and then we are skipping this guy and doing this guy. And the kernel size is 3, as in previous case. So because of the skips, what we have, instead of having this, like if in case of 6, we have 6 minus 3, right? This I minus K. We have 3 steps to do, right? But we are jumping the steps. That's why, because of these jumps, that's why we need to calculate the floor of this number. Because of these jumps, we are taking every second start plus 1, which is the same as in previous case. This is our first field, the first convolution applied at the beginning. For zero padding, we are just using the same logic. Our images are becoming the size of I plus 2p minus kernel divided to s. Again, why floor? Because the number might not, the input number might not be fitted into the kernel. So you might have some part of the image not included because of the difference of the kernel size and the last part of the image that you want to apply convolution for. Like this kind of problem might occur. So see that here we can't cover, actually here we can, but here, yeah, that's it. So we can cover this part, then we jump. We're covering this part, but we are not covering the last part. Imagine that if our image is a little bit bigger, so we are skipping this part. That's why, like, when the kernel, these steps are not fitted into the image size. You have some part of the image that you skip. What you can do to not to encounter this kind of problem, you can do appropriate number of zero paddings for your kernel, not to skip the informative part of the image. The pooling arithmetic, that is the average pooling and max pooling, like it's basically from mathematical perspective, from perspective of connecting your input size to output size, it's doing the same thing. The only difference is that you don't need padding in this case. So there is no this 2p addition, as in the case of the most general case where you have arbitrary number of strides, arbitrary padding, arbitrary kernel, and arbitrary input. So the pooling formula for output is just the same without pooling, without padding, or without this 2 times p addition. There are different like famous types of architectures for convolutional neural networks. Among most of the popular ones are VGG, ResNet, Inception, DenseNet, ResNext, maybe some more recent models like EfficientNet, NASNet. So let us go through these networks. So VGG is a simple convolutional neural network. What we have covered till now it is doing it. It is doing convolution. That element-wise rectified linear unit, if you remember, ReLU was 0 if the pixel value is negative, and the actual number that it is if the number is positive. Then you are doing the max pooling, and then at the end of the day, just standard fully connected layers to get the prediction. The ResNet is a little bit different architecture. Actually, it revolutionized again, like the architectures of neural networks. It has some strategy for initialization that you can read from the paper for ResNet, the K-mean initialization, which is a pretty interesting and important topic for initialization of the weights. Besides that, it's using the following things. So in order not to lose information from the input, after doing these all convolutional operations, at the end, you are adding your input to the output of subsequent layer. So every time this X is being moved to the next layer in order not to lose information, and in order for your input distribution to be stable. That's why you don't need batch normalization in case of ResNet, because the distribution, by adding these kind of things and by using K-mean initialization, the distribution is approximately the one that you want to be. Inception is another huge architecture developed, and one of the main features of Inception is that it has some temporary output, temporary loss function, and the final loss function. And the backpropagation, in order for you to do backpropagation, you add this temporary loss to the final loss, calculate the gradients, and do the backpropagation. The DenseNet is similar to ResNet. It is applied in medical image analysis most of the times. It is like performing pretty well in that domain. What is important for DenseNet is that it is like using heavy parameter sharing actually, because and every time the DenseNet is concatenating the input channels to the subsequent output channel. So every time you are moving all the information of that particular layer to the next layer till the end. That's actually the main difference of the DenseNet. You can read about all of them because I have written the papers for the reference of this type of architectures. I'll highly recommend to go through all the papers. And the last model, but not the least one from importance perspective, is the ResNext. The difference between ResNext and ResNet is in two things, actually. In case of ResNet, you have this one path and then adding your X to the output of this one path. In the case of ResNext, you have different paths. You linearly combine these paths, and then you linearly combine your input to the final addition that was made by combining these paths. So as final remarks for the machine learning lectures and data science as the thing that is that has a more general meaning than machine, because machine learning might be considered as a part of data science. It's a core data science thing, you know. Data science by itself is now considered as one of the most fascinating professions. Data scientist itself is one of the most fascinating professions for 21st century. Data science is incorporating the recent advances in machine learning, deep learning, in research to build your own business solution for your own domain, specific domain. Deep learning especially provide a great power of modeling. So you can model really, really complicated stuff. But with great power comes really great responsibility. And it's not only about the knowledge of the three main directions, the domain knowledge, the math and computer science. One actually needs to make business out of that knowledge. So the true Venn diagram, which is not the one that I've shown you at the beginning for data science and machine learning inside it, is the following. because it combines both computer science, neuroscience, psychology, economics, mathematics, engineering, and actually many different stuff, additional stuff. That's like why data scientist, it's a hard profession, and it really needs, really need to spend a lot of time learning all these parts and combining them to a business valued model. This is actually the reference list I've promised to speak about. So what books I'll recommend for you if you are like a beginner, and for you to like go deep into it. So I'll recommend starting with Python, since Python is the basic technology, the most popular language nowadays used for machine learning. There is also an R, Java, C++, but Python is like right now most popular one, and there is no stopping of that popularity for the coming like 5-6 years. The Python would be leader in this domain. But there are also another languages like Julia, Go, and especially Swift that many big companies like Google are making an accent on. So after maybe these 5-6 years, maybe the Python would lose a little bit its share to Swift, the same Swift. But for now, like this is like the go-to language that you need to study. After learning Python, which you can do by reading the following book, Mark Lutz, Learning Python. This is like the best book on Python. It teaches literally everything that you need to know about Python, and even much more than you need to know to apply, to use Python in machine learning. Then I'll recommend to go through some introductory statistical books, like classical book on Introduction to Statistical Learning offered by Hasti. This is like a really good book for introduction level. If you already know statistics, you have some basic understanding of statistics, you can go more in towards more advanced way of learning statistical learning. You can read the Bishop book, the Bible of machine learning, which is called Pattern Recognition and Machine Learning. They are the Bible that is really a good book for really advanced machine learning, and the same deep learning, because deep learning is being incorporated in these books as well, but to a lesser extent. You can go to this book, Computer Age Statistical Learning, but actually there is another one as well. This one, The Elements of Statistical Learning. This is the other Bible along with Bishop that one is to learn. The deep learning book is pretty good, and there are actually no analogs to this book till now in terms of the overall thorough coverage of deep learning topic. And as an introductory book to machine learning, I would also recommend the Rashka book that incorporates the practical coding with Python and practical examples, code examples of machine learning models. This is a really good book, and actually many stuff from this lecture is taken from this book, especially the first part of the lectures. So that's actually it. Start with Python, go to Introduction to Statistical Learning domain, learn more advanced stuff, and learn the coding, the practical coding, after you know the main concept of statistics, machine learning. Also, I'll highly recommend to go deep into the algorithms domain, because again, like data science is going to more computational stuff, as I've mentioned already. And you as a data scientist, as a core data scientist, you need to be really good at algorithms, because you are also doing some engineering stuff. You are not only like developing the models, you are helping to integrate these models. That's why like the algorithmic knowledge and knowledge actually of low-level languages like C, C++ is a pretty desirable skill nowadays in the market. So thank you all for coming to hear this presentation, and if you have some additional questions, I am ready to answer them.